All right, ladies and gentlemen, if you're watching this, then you should have already done the virtual investigation, molecule shapes, and worked your way through what the difference was between linear, trigonal, planar, tetrahedral, molecular geometry, bond, electron geometry, etc. You will have also worked your way through what electron domains are, and you have one shape that has two electron domains, two shapes that have three electron domains, and three different shapes that have four electron domains. And you will have also by now realized that double bonds and single bonds do not matter as far as valence shell electron pair repulsion goes. And that's pretty much where we should be right now. So this is actually just to draw it all together and put everything together into a single place so that you can see it, all right? And so you will have already done the Lewis structures and molecule shapes and realize that certain molecules are have certain shapes. Okay, so to pull it all together, I took these screenshots from the PhET simulation and I'm just going to go through them real quick. So here we go. The first one, you're taking a look at the things that are hanging off the molecule. You have 1, 2, 3, 4, and all of them are bonds. So we have 4 electron domains. We have 4 bonds. We have 0 lone pairs, which gives us a molecular geometry of tetrahedral and a bond angle of 109.5 degrees. So a bond angle of 109.5. All right, next one. We still have 4 things hanging off of the central atom. So we got a 1, 2, 3, 4. So that gives us 4 electron domains with only 3 bonds and 1 lone pair. That gives us a molecular geometry of trigonal pyramidal. And a bond angle of less than 109.5 degrees because that lone pair is big and it kind of pushes down on both sides and compresses that bond angle. So we have a bond angle of less than 109.5 degrees, probably around 107 degrees. All right, next one. We have 4 things hanging off the central atom. So we've got a 1 and a 2 and a 3 and a 4. So we have 4 electron domains, but we've only got 2 bonds and we've got 2 lone pairs, right? 2 bonds and 2 lone pairs. That is called bent because that's the shape right there, right? So that was bent. This one right here is a pyramid with a bottom that looks like a triangle, but this guy right here is bent. So bond angle significantly less than 109.5 degrees. And we say significantly less because this lone pair squishes that one down and this lone pair squishes that one down. And so we are going to have a bond angle that is less than 109.5 degrees, probably around 104 or 105, something like that. Now, those are all of the ones that have 4 electron domains. Actually, let me use a different color for that. Okay, so those are all the ones that have 4 electron domains. And so I will pull those together. With that color. All right. Now, next, moving on to 3 electron domains. So this guy right here has got 3 electron domains. 1, 2, 3. All of them are bonds. None of them are lone pairs. That is a shape that we call trigonal planar. Bond angle, 120 degrees. Because it's a circle cut into 3 parts, right? Like the Mercedes symbol, yeah? All right. Next, we have 1, 2, 3 things hanging off the central atom. Those are 3 electron domains. 2 of them are bonds. 1 of them is a lone pair. That is also called bent. The bond angle is less than 120 degrees because, again, that lone pair pushes on those, brings them closer together. It has a lower bond angle. So that bond angle less than 120 degrees, probably somewhere around 118. Those guys are the 2 that have the 3 electron domains. So I'll pull those together with that color. Yeah? All right. Last one. This only has 2 things hanging off the central atom. Electron domains are 2. Bonds are 2. Lone pairs are 0. That is linear, right? It's just a straight line. And of course, because it's linear, bond angle of 180 degrees. So bond angle 180 degrees because of course that is a line. And that's my final one. So I'm going to pull it together with that color. And there you are, your overview of valence shell electron pair repulsion theory and molecular shapes.